702 and Cape Talk.
The Naked Scientist.
Good morning to you, Chris.
Good morning.
Our science story is a fascinating one. Bioengineers, how close are they to lab-grown lungs?
Yeah, amazing this, isn't it? We know that millions of people around the world need organ transplants. We know that thousands, if not tens of thousands, if not hundreds of thousands of people die waiting on waiting lists for organ transplants. And this includes heart transplants, lungs, livers, kidneys, and so on. The big challenge is that there are just not enough donors. And often the people who do die with organs that could be used aren't willing or have not indicated that they'll be willing to donate their organs. Also, many of the organs that we recover from people by the time that they've died are not in a fit state to be transplanted. And this is why we have such an acute problem. And what scientists would really love to be able to do is to grow us new human body parts in order to replace those that have clapped out. We're a step closer this week because Joan Nichols, who's a researcher at the University of Texas Medical Branch, what she is publishing is a technique for growing very large lungs of human size and demonstrating they can be successfully transplanted into pigs. Now, it's very early doors, this, so one has to interpret it cautiously. Small numbers of animals, just 4 pigs that they've done this on. But what they do is they take a lung, and at the moment they're just using another pig lung, but you could imagine how you could take a lung from anywhere. They decellularize it. Now what that means is you put it in a special solution that can remove all of the cells that are there, and it leaves behind a scaffolding of connective tissue that's a lung shape, and also, critically, has the right guidance signals that would direct cells, if they're applied to it, where to go, what to turn into, and how to grow and organize themselves. They then take all of the cells from another lung, put the scaffold into what they call a bioreactor, which is basically a big vat of a culture or growth medium with growth factors and oxygen added. They then add the cells, and they do it in a certain set of stages, so you put the right cells in at the right time. The cells go onto the scaffolding, which has been pre-coated with a special hydrogel, a sticky material which has got growth factors in it. The cells take up residence on the scaffolding, and then over a 30-day period they turn into an immature lung, and this the researchers were then able to implant into one of their 4 pigs, and they were able to demonstrate that these animals will survive up to 2 months. They've only taken the experiment to 2 months at the moment, but the lung seems to be okay, the tissue seems to perform, the blood vessels all work, it can be plumbed in, so the next stage will be to go a step further and see if it actually works properly as a lung, not just being wired into the blood supply, but also can do gas exchange. But this is really phenomenal because it gives us an opportunity now to begin to push the boundaries of actually taking, say, a human lung that wouldn't be suitable for transplantation right now, getting the cells off of it and getting rid of those, and using that scaffolding to then repopulate it with new healthy cells and then put that into a person. So we're very close to this now. I think this is a wonderful piece of research. It's in Science Translational Medicine this week.
Wonderfully exciting. Andrew, good morning.
Hello, you see this? Dr. Chris, I would like to know why the sun is called a second-generation yellow star. And I would like to know which ones are the first-generation stars or yellow stars. And had it been a white star, would it be emitting more heat than it does now?
Hi, Andrew. When we talk about stars up in the sky, there's something like, in the universe, there's something like 100 billion galaxies. And in each of those galaxies, there's something like 100 billion stars, just to make it simple. So if you gaze out in the universe, we think there's one followed by about 22 zeros, stars out there. But they're not all the same. Stars come in a range of different shapes and sizes. And our star, the sun, is fairly small in comparison to many that you find out there, but the size of the star affects how big it is, how hot it burns, how fast it burns, and therefore what its ultimate fate is. And small stars will burn for a really long time, really slowly, but they're quite cool, as in they don't produce a huge amount of heat, and when they end their life they just shrink down to a little cinder. There are other stars which are very, very large, maybe 100 or more times the size of our own sun, and they burn ferociously hot, very fast, and they end their lives catastrophically with an enormous supernova explosion. Now, when we talk about star generations, we also are thinking about the age of the universe, because the universe is about 13.8 billion years old. Our star will burn for maybe 10 billion years, and it's currently about 5 billion years old. So it's halfway through its life. So in the universe, we've got generations of stars that were some of the first stars to form when the universe was really young, and then we've got newer stars being born today. So we talk about different generations of stars that have come along from the time that the Big Bang began. And it's all to do, the life and death of those stars, with how big they are, therefore how much fuel they've got, how much gravity they've got compressing that fuel, and therefore how fast they burn off their fuel.
14 minutes after 10, if you've just tuned in, you're of course listening to the familiar voice of Chris, the Naked Scientist. Oliver, good morning.
Morning, Eusebius. Quick question, easy one. Why is yawning contagious?
Hi, Oliver. When you say it's an easy one, I think we should invite you to answer it.
Yeah, that's exactly what I thought.
No,
well, when you're talking about stars in the sky compared to something
fair
yawning,
enough.
it's quite
Yes,
simple.
It does seem somewhat more mundane, doesn't it, when we've just been discussing the origin of the universe and the stars that are there. The answer is that we don't know precisely why it's contagious, but we do know that it appears to be quite common, not just amongst humans, but other species. Someone wrote to me the other day and said, "Can you catch a yawn from your cat?" And he had actually said that he watched his dog or cat yawning and it made him want to yawn. The answer is that yes, other animals do yawn, and they yawn contagiously with us as well. So it's a visual thing. When we see people yawning, it makes us want to yawn. There are some theories. One theory is that this has an arousal or an alertness provoking effect. And one of the reasons why it may do that is that when you yawn, it has a brain cooling effect because it draws cool air over the nexus of blood vessels close to your brain. And this can take away some of the excess heat from those blood vessels, helping to cool your brain down. The brain temperature rises with fatigue. So if you are tired and your brain temperature goes up, you can offset some of the fatigue-inducing effects of that thermal increase by breathing in some cool air. One suggestion is that if you're sort of winding the clock back to our evolutionary origins, if you are a group of people, humans are all sitting together as a social species, we know that we're better off in numbers than operating in isolation. If one person's feeling fatigued, it's likely that the others are too. So if one person yawns and makes themselves more alert, then other people catch that yawn and other people yawn sympathetically, they also will become more alert. The likelihood of everyone dropping off to sleep and then becoming lunch for a wild animal is reduced, and that might be one reason why yawning has evolved to be contagious. But it doesn't appear to be just humans. You can catch yawns off your pets, and your pets can catch yawns off you, as far as we know.
Mervyn, good morning to you. Welcome to the show. What do you want to ask Chris?
Hi, thank you very much for the time. I've heard that the moon is moving away from the Earth. The distance is increasing. Wouldn't gravity supposed to be pulling it back to us? And what will the result be to life on Earth if it is moving that far away?
Thanks for the question. A very interesting point that you've raised there. And we know that the moon is moving away from the Earth at roughly 2 centimetres more or so every year. And we know this because one of the Apollo missions put a mirror on the Earth's surface, and scientists are beaming a laser from the Earth's surface out to the moon's surface, bouncing it off that mirror and timing how long the light takes to make that journey, because we know how fast light travels. So if we time the journey for the light to get there and come back, we know very precisely how far away the moon is, which is how we know it's moving away from us. The question is, why is the moon moving away from us? The moon's about 4.57 billion years old. It formed when the Earth was very young, first forming itself, because two planets were on roughly the same orbit. They collided, and this other body called Theia rammed into the Earth and ejected a lot of material from the surface of the Earth, which then formed a big envelope or shroud around the Earth, and that shroud slowly coalesced to form our moon, and this is why the moon is so big in proportion to our planet. But the moon, as it's quite close to the Earth, is obviously sitting in orbit around the Earth. It takes a month for the moon to go right round the Earth once, but the Earth turns inside the moon every day. So the Earth turns once every 24 hours, and that's why we have tides, because the moon is pulling water on the surface of the Earth towards itself. But because the Earth is turning, the bulge of water on the side of the Earth close to the moon is actually slightly ahead of the position of the moon in the sky, because the Earth is turning and it's pulling that bulge with it. So what that means is that there's a very slight torque or pull on the moon from the bulge of water on the Earth's surface, which is slightly ahead of the moon's position. And that means that the moon is feeling an acceleratory force from the Earth's surface. It's a bit like you whirling a ball on a string, and you whirl the ball a bit harder, it tries to pull the string through your fingers. So the moon is actually getting a bit of energy all the time from the Earth's spin, and this has the effect actually of making the moon move slightly further away from the Earth. So that's why the moon is moving that 2 centimetres or so away from the Earth every year. It's going to take a really long time, though, before the moon goes any appreciable distance. It has made a difference, though, because when the moon was much younger, it was much closer to the Earth's surface, and we know that because we can see the patterns of the tides that it made written into the fossil record. You can see the heights of those tides, which would have been huge in comparison to today, because gravity obeys an inverse square law, so the effect would have been magnified historically. And as the moon moves away, our tides will become slightly smaller, but because it's creeping away ever so slowly, it's not actually going to make a big consequence for us or anything in any time soon. So don't worry, we're not going to lose the moon, but it is moving away from us.
702 and Cape Talk.
The Naked Scientist.
Chris, can I ask you just a question before we go to the lines about science education? Just a thought that's occurring to me. You know, talk radio in this country is dominated by men, sadly, but even by the normal standards of male dominance, I find that 90% upwards of questions about science on this segment tend to come from my male listeners. Now, the women can also tell me why. And I wondered, in your experience with public education around science, and also whether anything is done in the UK, who it is amongst boys and also among students that take an interest to some of the scientific inquiries that you are trying to popularize in terms of the gender. Just a thought that I had.
A very interesting question, this, and people are obviously investigating this in many countries because they also have observed that there is quite a strong split. The problem is not one of getting people of both genders interested in science, though. And in fact, we don't have a problem recruiting people in Britain and in Australia, where I've looked at the numbers very closely because I work in both places. We actually find that, in fact, going to university, going into higher education in Australia, 65% of the people who go into university are female. So we don't have a problem attracting girls into higher education, and we certainly don't have a problem attracting women into higher science education. If you look at the number of PhD students in Britain and in Australia to, comparable economies, actually the women are equivalent, if not slightly outnumbering the men. In medical school in the UK, about 55, maybe 56% of the people who get into medical school are women. Then you ask, well, what happens to all these people further up the chain? Do they carry on and become professionals in that space? And the answer is that after they get their higher qualifications, there is an exodus. So the question we should be asking is not actually how to push people into these things, but how to make the system change in a way that means that it is more supportive for everybody. Because what does happen is that people go off and have babies. And when they have babies, the system is completely unsupportive for family life, whether you're male or female. And actually, if you think about it, you've got a grant, and that grant is funding your research, and the clock is ticking, and you go off and have your maternity or paternity leave. It doesn't matter who goes off and has their leave. And then the grant doesn't stop. The world of research doesn't stop. And it's very hard to then juggle having a young baby, having families, getting grants and keeping your career on track. So lots of people think, you know what, I don't think this is the life for me, or I don't think being professor of surgery is the life for me because I can't walk off the operating table and go and pick my kids up from nursery at 5 o'clock. And so the system selects for a very specific group of people. And until we fix the system, you can have all of these ambassadors and you can have all of these people in as role models and everything, but the system is broken. And until we fix the system, it's actually just always going to relapse to type. So I'm very, very pro kind of helping to improve the system, because if we improve the system, everything gets better for everybody.
Makes sense. Mfundo, good morning to you. Welcome to the show.
Well, I'm enjoying that. That's very interesting.
Oh, there's something. I'm chuckling partly because I can see here the question that you wanted to ask you, and the fuzzy noise there actually, in a circuitous way, is related to a question. She wanted to know from you why it is that the radio never appears to be in sync, like when you switch between devices from your phone to the old wireless in the room or in the car. there may be a lag from the one device to the other one of like 1 or 2 minutes.
Well, hopefully not 1 or 2 minutes, but certainly some seconds you would notice a difference. Not so much with the old-fashioned radio kits, which were analog, where the analog signal comes in, it gets very quickly processed through the electronics. There's very little difference in the way that they're going to process things, and so you get a sound which is pretty much in sync across all devices. But in the digital era, there are a whole range of reasons why there may be latencies and different latencies, in other words, lags between the signal coming out of the transmitter and then coming out of the speaker in your device. Now, audio processing is very fast these days. You've got microsecond delay latencies in these devices. But if, say, you're tuned into the internet, because the internet is a whole connected or interconnected network of stations, then the information can have different latencies or different delays in how quickly it arrives at your computer. And at your computer, it then gets put back together, a bit like you building a picture from a mosaic. Lots of little pieces are all reassembled to make the big picture. Then that all takes time. And the route that the information's taking, say, from the source to your computer might be different to the route that it's taking to someone's digital radio or from one radio to the next. So there's processing delays in actually getting the information to your device, there's transmission delays, and then there's recompiling delays. And these all differ between different devices, and so that's why you get variable lag in this digital era between different devices.
Okay, Theo, good morning to you. Thanks for holding on. What did you want to ask?
Good morning, Dr. Chris. You're not allowed to put metal objects in a microwave because it sparks, yet the microwave is lined with metal inside.
Yeah.
Why is that?
Hi, Theo. Well, actually, it's not strictly true that you can't put metal objects in the microwave. You have to be careful about what sorts of metal objects. If you put a spoon in your cereal bowl, say you're making some porridge or something, and you stir it with a spoon, actually a big, thick, heavy-duty steel spoon is not going to cause a problem. And that's because when you put the spoon in the microwave oven, the metal will act as an antenna, and it will pick up the microwaves and convert them into an electrical current flowing inside the metal. Now, a big steel spoon or knife or fork or something has very low internal resistance, so there's this current's going to go flowing backwards and forwards, no problem. It will just make the metal hot. Not safe, not sensible, because you might burn yourself. It's probably not going to cause a big problem, though. When you put something like a crisp bag, which we've done on our website, nakedscientist.com/experiments. You can find us doing this. Or if you put, say, a gold-edged crockery, not that I've got any of that, but you might have, if you put that into the microwave oven, the very thin metal actually is a relatively poor conductor because it often has little gaps or breaks in the metal, or the metal very quickly heats up and distorts and deforms and opens up a gap. And what happens is that this charge, which is surging around trying to make a circuit, hits this gap and it has to jump over the gap, and that's what makes the spark. And that's why things go zap and snap in the microwave when you put little bits of metal in there. The inside cavity of the microwave oven is metallic because what it's effectively doing is acting as a mirror. And it's producing microwaves on one side of the oven. Those go across as a wave with a wavelength of about 12.5 centimetres across the inside of the oven, and then they hit the opposite side, bounce or reflect off, and come back mapping onto themselves. And that makes what we call a standing wave, which is how it does the heating effect. The grill on the front is almost like a sheet of metal, except it's got little holes in it, which enable you to see what's going on, because the size of the microwaves are much bigger than the size of the visible light waves. So the visible light can get out, but the microwaves can't come out and cook you. So it doesn't matter that the microwave is made of metal. It's actually there to shield the room and stop the microwaves escaping, and also to reflect them back onto themselves so you get good cooking.
Okay, we can squeeze in one final question. There are two callers. Pick a number, Chris, 2 or 8.
I'm going to go with 8 this time.
Okay, out of interest, the question for number 2 would have been about geothermal energy going further into the earth. Why can't that be the case? But the number 8 has won the lottery. Richard, what is your question for Chris?
You talked about stars and the life of stars and how they have the end. But how does a star form in the first place?
Okay.
Morning, Richard. Well, what happens is that the universe is awash with gas and dust particles. The products of the Big Bang were chiefly hydrogen, lots of that, some helium, and then a whiff of lithium, those 3 elements. And so the universe has lots of these bags of gas and dust wafting around all over the place. And under the influence of gravity, this gas begins to associate and coalesce. something might give it a nudge to encourage it to collapse onto itself a bit more. So, for instance, we think our sun got started because another star in our nearby cosmic neighbourhood blew up, created a shockwave, and that pushed some gas together and encouraged the effect of gravity to dominate. And once you've got a big body of material beginning to fall in on itself, it then attracts even more stuff and more gas, which compresses the gas that's already there. And you can see how this is going. When you get to something which is as big as a star, actually it's so heavy, so much mass, that there's so much gravitational force pushing in and accelerating the particles in the centre that it can overcome the natural repulsion of the particles, and they begin to fuse. And you begin to fuse hydrogen initially, and hydrogen, 4 hydrogen atoms fuse to make an atom of helium, and as they do so they release a lot of energy. And once you've got some energy, you start making particles ram into each other even harder, so the whole thing goes into a sort of positive feedback loop, making a fusion reactor. And so that's how a star gets ignited in the first place, and it will burn for as long as it's got fuel to burn. Initially it will burn the hydrogen because that's the easiest, and then as it starts to make more complex elements like helium, lithium, beryllium, boron, carbon, nitrogen, it begins to do what we call nucleosynthesis, and you add more elements to bigger elements and you get even bigger elements up to a point of about iron. And then when the star gets to the end of its life and goes bang, if it's a really big star and has a supernova, you get such a powerful shockwave when that happens that you then make even more big heavy elements like uranium in the outer shell of that star as it blasts itself to pieces. And the gold and all the other heavy stuff that's in your body right now was made because another star was born, died, and blew itself to pieces and blew all that stuff out into space, which eventually coalesced in our neck of the woods and made us billions of years later, which is an extraordinary thought, isn't it?
Chris, thank you so much for sharing your scientific knowledge with us.
It's been a pleasure. Thanks, everyone. See you soon. Bye-bye.